Look very closely. Beside my head will be a water tank. And when I finish the presentation, it'll be obvious why there's a water tank. So I want to try to just cover some things today that are very relevant: water, energy, carbon, chemistry of cleaning solutions. But I want to finish with some solutions. And I don't mean chemical solutions, I mean real solutions. So let's quickly begin. I want to give you some perspective of not only sustainable, but as we'll see in a minute, what we refer to as self-sustainable. How to build a building which was completely off the water grid, how to build a building completely off the energy grid, and hopefully a building which has zero carbon footprint and zero carbon emission and zero sodium emission and no phosphate discharge and no nitrate from groundwater, all of those things in a design, and it'll become apparent. So what's the need? In the world of teaching, you've got to establish the need before people pay attention. So let me show you the need. We had speakers this morning, but I have a different perspective. This is the atmospheric CO2. This is 1900s. We're about 300 parts per million in the atmosphere. This is the increasing outer spiral of CO2. We hit 400 in the last year or so. If you contrast that, this is the ice cap in September in the Northern Hemisphere. It used to be 11 million square kilometres. It used to be. It's now spiralling inwards to less than 5. I don't expect to see global warming while we're melting ice caps. You can have the conversation and argue about climate change. There is no doubt. So if you have a conversation with someone who's a skeptic, please understand what is fact and what is reality, and this is the reality. When we disappear with the ice cap, we really will see global warming. So we're coasting along right now, but there is no doubt. You've heard of the International Panel on Climate Change. This is a paper that was published a number of years ago, 2007. This is the ice cap extent in millions of square kilometres. Notice in this example from 1900, they're at about 9. Their model, which is used for the temperature projections, actually predicted the melting. And what it says is by 2100, we'd be back to about 2 million square kilometres. What I want you to recognise is that's a theoretical model. The actual data is 50 years worse. We're at a point where the model thought we would be 50 years from now already. Do you understand the importance of what I'm saying? Okay. And if you actually go back and plot the area, extent, square kilometres, to the concentration in the atmosphere in September, you get a relationship which has 0.95 correlation coefficient. We lose 1 million square kilometres of ice extent every time the CO2 goes up by 15 parts per million. That's now down to about a decade. Several of us in the room have experienced in their life more carbon emissions, as people have pointed out. Several of us in the room have experienced more ice cap melting than any generation in history. Can we own up to ownership? So that's the need. So what are we going to do about it? We've got to change it. We've actually got to go backwards. What we need is carbon negative industries. In order for the wine industry to be carbon negative, we have to own up to our real carbon footprint, and we have to try to make wineries which are carbon zero, so that the consumption by a vineyard makes the grape wine industry incredibly carbon negative. The brewing industry can't say that. The spirits industry can't say that, but the wine industry can say that, and it should, and this is your opportunity. So that's where we're headed for. I'm simply going to try and address this bit today, and together with other factors of sustainability. So ideally, we'd build new wineries. They'll be off the grid. They could be in remote places. They could be off a water grid because they may not have a good water source. Or what they used to have as a water source isn't available or isn't good like it used to be. There are other reasons, but could you operate a winery off the water grid? Could you capture the CO2 from fermentation? Yes. And can you use cleaning chemistry that doesn't contribute sodium into groundwater? Yes. More important, can you change your practices so that when you use water to wash a tank, you will capture it, filter it, and use 90% of it again, and do it again, and 90%. And by the time you've done 10 tank washings, you've used a fifth of the water. Now you've generated a fifth of the wastewater. Now you could build a winery in a dry place like Davis, 400 millimetres a year, half of which we got last night, I think, in a Porto. You could build it in a dry place and still have enough water, because you've changed your practices so that you could build a winery where you didn't need so much water because you're going to use it over and over again. And now, because you want to use membranes to recover and reuse it, the water has to be very pure. Now you'll go to rainwater because of its purity, so that you can capture it and filter it and recover it, and you can do it again and again without fouling your membranes. Does that make sense? So what I just told you is, you could build it in a dry place. You want to use your water 5 to 10 times. You want to make sure it doesn't have mineral content. You don't want to put a whole lot of stuff into it, and you actually want to discharge it to flush the toilets in the tasting room before you're finished. There is no wastewater pond. Okay? So let's look at energy. Typically, we have the CO2 footprint associated electrical energy on a grid, depending on where you are, what that is. Moving towards on-site PV, photovoltaic, and lithium battery storage. So now we want to capture 8 hours a day. We want to operate 24. We're going to have it stored somewhere so that we can do that. And so this morning, Miguel was talking about the practices at Torres. He drives a Nissan Leaf electric car. I drive a Tesla. The lithium batteries that used to be in his Kia are now, I'll show you, operating a winery in Davis because they're reused, they're recycled. So keep in mind that Germany has a target of 1 million electrical vehicles, I think by the end of 2020. After 3 years of use, they swap the batteries. In 2023, there will be 1 million sets of batteries available to operate wineries who want to use them for lithium storage. Are you with me? So I'm selling shares in... Never mind. Many people have moved to that because maybe economically it paid back quickly. The question now is, what's the economics of that? I'm interested in the concepts of it. But we want to store the electricity as electricity if we can, but there's a penalty for doing so. To convert it and to bring it back again, we lose some. So it's convenient, but there's an efficiency question. We'd like to use the energy in different forms. If we're going to do cooling with electrical energy in a refrigeration system, why don't we make ice cubes and bank it, thermally bank it, so we don't need the electricity later to get the cooling. And if we had presses which were running high-pressure bladders, would we make compressed air and store it so that we didn't have to run the compressor to run the press? And if we were making inert gas blanketing, would we make the nitrogen and store it? And now the question comes, what are the storage forms for your photovoltaics? And there are several. And during harvest, we would invest and build in storage systems so that the operations would be able to perform at night during harvest when there is no sun and we're not on the grid. But we also want to change our process conditions. We want to run cold water instead of glycol. We don't want to run colder than 5 degrees. We don't want to make crystals inside the tank because we'll come along later with hot water and caustic to clean it. And then we'll have sodium in the discharge and we'll use hot water. And we don't want to do that, and we don't want to do that, so we better change the temperature of the jacket so we don't make the crystals in the first place. You with me? The design of the coolant temperature in the jacket is affecting the sodium content of the wastewater. Okay? Don't ask the guy that does your refrigeration system about that, because he's not concerned with the sodium, and don't ask the wastewater guy about the sodium, because he had no choice in the temperature. But I hope you can see they're connected. We want to use efficient cooling systems like pulse cooling, where we will only put cold liquid into a jacket to take heat out, provided it gets heated up. We want to return it warm so that our refrigeration system works properly. Returning it cold is self-defeating and takes up more energy. Do we want to have passive buildings and energy-efficient buildings? Certainly with respect to warehouses for barrel storage. I'll come back to that in a minute. This means there's no air conditioning load. This means there's no heating load. There's no carbon footprint from having a heating system for gas or fuel, because you built an effective building which in the wintertime didn't need to be heated, and a building which in the summertime didn't need to be cooled. Now you can use less energy. Now you can be off the grid on your solar array. So we use nighttime temperature in a very hot place called Davis, and I'll explain to you the thermal envelope in a minute. For water, we want to do on-site capture. We like to use our own water, not somebody else's. It's very hard to talk about sustainability when you go and get the water out of the river or out of an aquifer. You can do it, but it's hard to talk about being self-sustainable. So we capture rainwater. But because we don't use it for 6 months, we have to store it. So we use rainwater tanks. So we'll harvest the rainwater in January. I can't imagine how much water we would have got last night. Doesn't matter. But that would have been the purest water you could get, purer than anything out of any tap system that you'll be given. And so we've got to understand the purity of what that means in membrane life, what that means in using water multiple times. That's why we want rainwater. So we want to switch from cleaning chemistries which are potassium-based for plant reasons, not sodium. We want to use chemistries that don't have a BOD or COD contribution in the wastewater pond. Those are potassium bisulfate and potassium hydroxide. These are dry pellet forms. We don't have lots of solution. We only make up the solution when we need to. So we're very confined, very collected. And if we mix these two together, it becomes pH 7. It's potassium sulfate. Sulfate's the major anion in most groundwater systems. Potassium is the preferred cation in plant systems. And so when you put a potassium sulfate solution on a vineyard or a soil, we're not worried about the conditions we would be with sodium or phosphate or chlorine or other things. And we use hydrogen peroxide, so there's no ozone, and yet we can kill at ambient temperature. We'll see in a minute. We want to capture the fermentation and ideally sequester it on site. Eventually, we'll be looking at the release CO2 from composts, and we'll want to understand aerobic wastewater treatment and the CO2 footprint, which is related to the carbon introduction of the BOD for wastewater. But I'll come back to the wastewater in a minute. We actually probably have to eliminate aerobic pond treatment. And you can argue about the CO2 piece, which we will today, but the other problem with that is the nitrogen from amino sources in yeast and pulp and juice is going to end up as nitrate. We're actually putting nitrate into the water that somebody else might drink. I just want you to understand the ownership of that and why we've got to stop doing it. So we'll probably go much more to anaerobic conditions like Miguel was referring to this morning. Methane-based conditions captured so that we don't use nitrate formation ponds. And then we want to use gas in stored forms. Reverse osmosis water becomes an energy bank. It's something I did with the energy when I needed to, so I didn't have to use it later. I mentioned compressed air, I mentioned nitrogen, and we generate peroxide. So the concept here is not just rainwater, but multiple use, and that's the rainwater purity. And that purity, we have no hardness and we have no silica content. silica is the thing that fouls membranes. And so groundwater silica is shortening membrane life. That's increasing the cost of using rainwater. If you start with rainwater, no silica, you've reduced your cost because you've extended your membrane life. So just so that you understand what we're doing, we take rainwater and we filter it to this level. And what that means is we would take out all yeast and bacteria and molds. So if you're worried about bacteria, that's gone. This is sterile filtration. Except we're also going to filter out every virus that you're worried about. I'm not worried about a dead bird and West Nile virus off the roof because I'm going to filter out the virus and the bacteria in the first step. I'm not worried about measles, HIV, anthrax, rabies. Sorry, I know this is a wine conference, but these are all viruses which are in water systems, which we typically use the UV or chlorine to get rid of. We don't want chlorine in the environment. We don't want to use UV because it doesn't work on all of these. But if we use RO filtration, all of that series is eliminated. So is the pesticide residue from 6 miles away in the rain, and so is the hydrocarbons from the freeway in the rainwater. Those are all gone in a single step when I do RO filtration. So if you want to put that into context, it's like doing desalination. So we do desalination on rainwater. That was a joke. Okay, oh, never mind. We'll come back to that later. What that lets us do is use ambient temperature, not hot water. We can get 5-decade reduction in E. coli. That's a lot of killing of E. coli. We use these matched solutions, but we've eliminated sodium phosphate from discharge. Think of algae bloom in river streams, and think of sodium in groundwater. And there's no contribution of these to the pond. Blah, 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 blah. I'll skip those. So what's this? This is a death curve. Sorry, these are death curves. This is not a Star Wars movie. This is time in seconds in log scale. 60 seconds would be a minute. 120 would be 2. 1200 would be about 20 minutes. So think of this patient here as 20-minute contact time. If we used water at 50 degrees at 7, we can kill E. coli 1, 2, 3, 4, 5 decades. That means if you started with 10 to the 5 cells, 100,000 bugs, you would have killed them all except one in 20 minutes. Now, normal cleaning in the wine world, we'd be lucky if we get 10-fold or maybe 100-fold. So what I'm talking about is really efficient killing. But we're doing it at ambient temperature, 50 degrees, hot water, no, warm water. But if you switch to potassium hydroxide and you use potassium bisulfate at pH 2.3, now you'll notice a whole range of organisms, including E. coli, are killed 5 decades within 20 minutes. Okay? We don't need tons of chlorine. We don't need ozone. We don't need a lot of chemistries that you were taught to need, because the worst bug we're worried about, and we're not actually worried about it in wine, but in the world of food, we would have killed 5 decades in 20 minutes at ambient temperature. So there's no hot water, so there's no carbon footprint. Blah, 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 blah. And it's really the ability that we can filter. When you hear of desalination, you think of a lot of energy. Well, that's to take water out of seawater. To take water out of rainwater takes almost no energy at all. The concept of recycling is if we use the 90% factor, we went through 10 cycles, and we nominally say we used 100 volumes to clean a tank. Now, if we were to recover, 90 of them will be ready for the second tank, and we only use 10. And so the make-up water is 10 instead of 100 each time. And at the end of 10 cycles, we've used 90 additional. So we started with 100, we used 90, and we would have used 1,000. We're a fifth of the water. That's only if I stopped at 10. You with me? We could have kept going. So CO2. In the world of sustainability, there's a thing we have to, this is not a therapy session, but we have to speak about something that's been hidden. And we have to be a little bit more honest about what it is. but it's what's referred to as Scope 1. It's what's called your stuff, not someone else's, not the downstream chain, yours, okay? And in Scope 1, the biggest emission is fermentation. And of course, if you looked at several calculators that are used in the industry, it's a zero. There is no emission in Scope 1. We're going to change that because there is. You were just being misled, and we need to correct that. The point is, this emission, is the richest concentration emission of CO2 anywhere in the world. And it happens in our business, and we say we don't have to do anything because the grapevines will take it up. If you and I were serious about taking CO2 out of the air, we would never let it get in there. We would go to the richest source and we would capture it. Not take it out of the air at 400, not take it out the back of an exhaust pipe at 200,000 parts per million. You would capture it at 1 million parts per million. And it'd be ambient, and it'd be stationary, and it'd be ground level. All the things you'd want, but we don't have to do it because you've been told there's no emission under Scope 1. So this is the biggest emission. And we can talk about everybody else in the chain. It doesn't matter. It's called denial and reflection in the world of psychology. We're worried about this one. So let's go through and say why we would build a winery, capture them at fermentation, ideally sequester them so that that number is a zero. Now we have a winery which is zero carbon completely. It's this emission which is really the issue. And we're not going to try and claim this offsets from next year's grapes. We're simply going to say this is our emission and we should take care of it. It's about 1/8 of a tonne for every tonne of grapes. We generate about 60 litres per litre of table wine. In the case of port, by the time we ferment table wine, distill it into brandy, come back and fortify port, we're at about 120 litres per litre. It contributes about 80 to 90 grams on a 750ml bottle. Not the bottle, the wine emission that's in the bottle. And remember, the bottle is Scope 3. This emission is Scope 1. This is ours. But it is the most concentrated industrial release. And apart from conditions about worker safety in buildings and other things, we'll just talk about if we wanted to be zero carbon, why we had to capture it and sequester it. So we would capture it from the top of fermenters. We could be temporary pipe work, or it could be permanent, depending on aesthetics and practicality. There are alternatives of sequestering it to compress and condense, but they're incredibly energy intensive and can't handle a very big volume in a very short period, maybe 8 weeks. You can absorb it onto different materials, but you have to regenerate them, and the regeneration takes energy. So absorbing and using energy to release it and keep on using it, you'd have a lot of material for a very short period, 6 weeks. But if you could capture it in a relatively simple solution, and Miguel referred to this morning, and Torres as a company has been working on this for many years and given a lot of consideration. But essentially we're trying to capture it is the form of calcium carbonate. And you could use that calcium carbonate for other industries. We'll come to that if you're interested. And there may be some future. When we build a winery today, I don't care what the future options are. There are some solutions. We have to build a winery to capture. We want to be ready for when these things come around. And that's not changing 5 years from now when they come around. That's actually building a winery today so that you're ready. Blah, 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 blah. We'll skip this in terms of time. The difference between, I think, the approach that Torres took in the designs was not only there are different organisms that could use this CO2, so it's the captured form to deliver to grow the organism for protein or for biofuels or for sugar, carbon. But we want the calcium oxide, which is used after the regeneration, to come back to us. We don't want to be buying calcium oxide. We want to keep on reusing calcium oxide. And now the economics are quite different when you're recovering and recycling. This is a description, a process flow diagram that was done in a simulation package called Aspen. This has been done by a colleague, Ron Runnebaum at Davis. And it's a project which was funded primarily by the Jackson family. And it was an attempt to try to put together the systems and the components that are needed to build a little skid that would now sequester CO2 on site. And in the process now of trying to build that kind of activity. So our fermentation CO2 system is a fairly interesting one. We've got 150 200-litre fermenters, and we have 14 2,000-litre fermenters. And so typically it's a number of columns which are made of solutions of calcium oxide, and that precipitates quickly as calcium carbonate. We'd recover the crystals, we'd dry the slurry. We actually want that to come back as through the bed of resaturated calcium, ready for the next use. So we'd operate this kind of system during harvest, and we would actually pass it on to other people in other industries for their use. But we want the calcium oxide to come back. Efficient buildings. If we were unable to build stone buildings and we're unable to build buildings into the ground, now the question is above ground, how to make them very efficient. And that's really speaking about what we call very high thermal insulation envelope. Being able to use nighttime cooling, being able to displace at daytime in warm conditions during winter, and how to run a building with essentially constant temperature and therefore constant humidity, but not having the heating CO2 footprint and not having the energy load of an air conditioning system. So let me go through the examples of the winery at school, which embeds virtually everything that I've talked about into an example. It's the first LEED Platinum building in the United States that was a winery, as Jamie indicated. It was the highest scoring platinum building at any university in the United States when it was completed. The building was completely privately funded in 2009, which is the middle of the meltdown. So it's an exceptional building in many regards. But the certification is what we refer to leadership in energy and environmental design. This is what LEED stands for. And this is sort of the green gold medal, if you want, but it's platinum. So the Olympics will catch up one day. So here's the winery. We have an array of photovoltaics that generate energy. We store them in lithium batteries. That provides the energy source. We have an adjacent set of buildings that collect the rainwater, and we store them in rainwater tanks, filter them to RO. That becomes the water source for the cleaning. We run a system with bisulfate and hydroxide and clean in place and recover those solutions and refilter them. We're using both the water and the chemistry. So when I use the water a fifth of normal, I'm using the chemistry a fifth of normal. Okay? We capture the CO2 and eventually we'll sequester it. We make cold water from photovoltaics and an ice bed and only chase 5 degrees. We have a hot water system which is passive solar. We have the ability to run a fuel cell and generate hydrogen, complement that. This is not installed currently. And we can measure and monitor that system with a fairly advanced data system. This is the winery building. This is the brewery and the food lab. This building and its tanks are the LEED Platinum facility. The roof rainwater off these buildings goes into these tanks. These tanks are non-potable building water, toilets, landscape. This is 1 year for this building. So it was the first rainwater building to be LEED Platinum. And it was completely off the power grid the day it was opened. It, in the revision of the scorecard for LEED Platinum, this building gained 3 points by doing nothing because it was already over-designed for LEED. Okay? It was built to be 100% solar rainwater. LEED gave you points for 40 or 50% water, 40, 50% energy. This was a LEED building more advanced than LEED. Does that make sense? The second building here is what we refer to as the Jess Jackson building. You'll notice that it has another set of tanks. And in the corner here is the roof area is the roof area for the Institute buildings. This roof area catchment is for these tanks. These tanks are filtered through to RO to provide the water for cleaning the tanks in the winery. This is where the cleaning water goes back to be filtered and come back. This is where the CO2 gets piped across to be sequestered. This is where we'd make the hot water from solar, passive, and this is where we'd make the ice cubes for Ice Bank. So the Jackson building is the exposition building for the technologies which run a sustainable winery, but it's also a very advanced building in and of itself. So this is the Jackson building in profile, this is the winery. You can see there's loops going to and fro of cleaning water, of hot water, cold water conditions. The Jackson building has its own water system, which is the cleaning water here. It has the battery container for electrical storage. It was designed to have a below-ground rock bed as well, and that's the layout. So these are our 2,000-litre tanks. These are all capturing CO2. These are the small 150 research fermenters. When we're operating those, they also capture CO2. We typically run redox potential and Brix difference for online pressure difference for Brix, a Beaumet density. Our small fermenters are actually web-based and wireless and have been for years. And so we can monitor these systems very accurate and very precisely. And this red curve is a typical measurement curve for a fermentation. And the blue curve is a mathematical model fitted to that. And so typically by less than half the way through fermentation, we will fit the model. We will get the parameters and we can predict demand curve. The demand curve is the rate of fermentation. It's the rate of CO2 generation. It's the rate of heat requirement and release. By being able to do this on this fermenter and being able to do it on all 150 fermenters, I can anticipate how much ice I need to make today for the next 2 days. So the fermentation curve that the winemaker looks at, the modelling which is going to help us understand if it's sluggish or stuck, is the very same curve and model that is used in the application to pre-cool and make ice cubes 24 hours or 48 hours ahead, and to manage the CO2 flows from those fermenters. Same thing. The Jackson building is an exceptional building because of this passive design. I can tell you it's 2 degrees, but why don't I show it to you? So this is in Celsius. This is, I think, August of last year. 40 degrees, we have a few days at 40 degrees, but this is the daily variation in temperature over just over a week. It gets quite hot in Davis, but it also gets very cool. The temperatures in this line here are the temperatures in the building. So here's a building in Davis where it's 35 to 40 degrees outside and it doesn't rise by more than 2 degrees and it only needs 2 degrees of cooling each night. Okay? That's a building which doesn't take much energy. That's a passive, high efficiency envelope. That's the kind of buildings we build barrel rims of in the future. It has the different rooms and the systems. I'll come back to that. So we have a series of water tanks which the rainwater goes directly into. We filter those to RO level, reverse osmosis level. We can use that in processed water, hot water and cold water heating and cooling. We use it in the CIP cleaning systems. And when it's finished, we actually go to industrial, and that becomes what we'd use to wash the floor, and that goes to a biodigester or the next toilet tank. So we want this loop to go around at least 10 times. We want to keep on using last January's rainwater. And we'll invest the energy that we're making from solar so that we can. These are the famous water tanks. If we go back at the beginning, the picture of my face with the water tanks, that's the joke. These are the water tanks. It's better without the face. When we do the RO filtration, we use a system like this, fairly small. There's a box at the side here which measures total organic carbon. Total organic carbon is the measure of impurities in the water. If you went to a medical emergency, where's Beatrice, Typically, if they gave you an intravenous injection for glucose or salts, the water has to be 250 parts per billion organic carbon. Okay? So that's what we think of we need for our health. We've been generating water which is between 15 and 25 parts per billion, 10 times cleaner than you ever had injected into your veins. I'm not worried about bacteria. I'm not worried about viruses. I'm going to give you cleaner water than you've ever seen in your life, and that's what we use to wash the tanks. So 2 modules is enough for 1 million litres. We've probably filtered 2 million litres and we haven't changed the membranes yet. And in the world of membrane filtration, that is unbelievable. But it's because we use rainwater. In energy management, we have to follow this solar array, but we also want to, in fact, fill it into batteries, as I indicated, make compressed air when we need it, top up nitrogen when we need it, make ice, maybe run the CIP system, and maybe refilter the RO water as we need it. So we're going to use different forms. These all become storage forms, non-traditional thermal banking of energy, rather than just electricity on the grid and maybe a battery. The winery, for example, since it was open, this is 2012, typically runs at about 10 kW in normal daytime. So we would consume about 80 in the first 8 hours of the day. We would generate over 400 when the sun's out. Again, this is February. This is not July. This is February and Davis. And this is the 24-hour period. So you can see the building was grossly positive on a kilowatt-hour basis from day one. These are some of 108 lithium batteries. Miguel's Nissan Leaf car used to have one of these. There's a trailer with 100 of them plumbed together. They become the storage bank for our solar array. We didn't buy a Tesla wall. We actually built reused batteries into a storage system, and that's what that is. Come to cleaning water, we also manage that in terms of following, but the real issue is that we run these 2 pH conditions that are very different, that they're potassium-based and we use peroxide. But when we finish, that water is going to go to industrial water. It's going to go back to be used in toilet and landscape one more time, and that becomes our interaction of rainwater, processed water, cleaning water, and wastewater. In the absence of video, why don't I actually go to some suggestions? So, one of the problems, they were talking this morning about the business model and why people haven't sequestered CO2. So forget the dishonesty of the rating system for the emission, firstly. There's no value in capturing it because the carbon trading price is depressed, and that's because we gave out too many credits, and that was because there was no need to buy credits because we gave out too many, so the price is depressed, so there's no business model. Okay? The price of carbon in California has finally become a reality. Most of the wineries in the industry of California have exceeded their allowances. They're now buying on the auction. The price of carbon went up 3 times, 3-fold, in the last 3 months. There is now a training program for carbon in California after 15 years because you never had to because you got plenty of credits. So those days are over. Now there's the business model. So you're actually going to capture carbon and sell it, quite apart from being carbon zero and being sustainable. And that price will change, but it's probably not going to go backwards. So I'd suggest you support at any point that you can both international and domestic carbon trading systems, because that's the future of your selling of your waste product. We've got to get a proper calculator that includes this. Even if we went to the OIV site, the fermentations from emissions are not considered as Scope 1 emission. They have to be. And the international calculator that's been distributed through a group called FIVS also puts the emissions at 0. So we've got to get a proper calculator, and it's got to include fermentation. We've probably got to begin reporting our CO2 numbers truly, because currently this is put to 0. And we've got to get groups like major international carbon validation organisations to actually understand that it was put to 0, because they're doing evaluations and things for you, but they're using the wrong numbers because they've been told the wrong numbers. So we need to change that. And we need to discuss partial ownership. We had a bit of a conversation this morning about corks and recycling, and we could talk about on bottles, but I'd suggest that Scope 1 is completely yours. Scope 2 and Scope 3, a consumer owns part of that footprint, a retailer makes part of that footprint, the distributor owns part of that footprint, you own part of that footprint, and the bottle manufacturer owns part of that footprint. We haven't worked out what the fractions are, but it's not all theirs and it's not none yours. We've got to talk about partial footprint allocation and ownership, and we aren't there yet. You might want to establish an international scientific panel that talks about the carbon industry, of the carbon footprint of this industry. What we've been given is manipulated calculators by people who had a vested interest in political. And that was good, but those days are over. You might want to get a bit of science into those calculations and get them up to date. You might want to get across the boundaries that are the limitation to research projects. And I think Miguel alluded to this morning. Antonio mentioned it as well. How do you start funding projects in other countries because you want to and need to, not just because of nationalities and government perspective? I can't get funding to do carbon sequestration in California because I live in a state where the policy of the major industry is not to do it. So there'll never be funding. If I had come to the United EU and maybe gone to some other countries, I could have got funding. I didn't feel that was appropriate, but right now, this is what we have to do. You might want to consider joining forces with brewing. You would like to have the brewing industry capturing and sequestering because we would like to give them some CO2 from 6 weeks of harvest. But they're going to be operating 52 weeks a year, 24 hours a day. They will really need a sequestration system. And if we could just get them to start to do it, we'd have somewhere to send our sequestered material. So it's in our best interest to have them aware of this problem and take on the ownership of sequestering because they want to be our partner. Or, sorry, we want them to be our partner. You might want to establish a global competition or challenge. Imagine if there was an organisation that said $1 million a year, we'll have a conference, we want all your best projects, we'll award a prize for the best advance in the last 12 months. It's only going to cost you $1 million, but I'll bet you what, you'll get a whole lot of people competing, and you'll get a lot of companies competing for the chance to get $1 million, and you'll get a whole lot of stuff done really quickly. But make sure you've got a scientific panel and make sure it's global, and you could do that. So I want to leave you with some final thoughts. The first is from Gandhi. It's probably one that you've seen before. But commonly people say, well, we can't do that, it's too difficult. Think of Gandhi. How else could you get an imperial power out of your home country, pretty much under your own influence? But whatever you will do will be insignificant, but it's very important that you do it. So capturing the CO2 from your fermenters will be insignificant. You can finish it, sorry. That was a chorus. Stand up, I want you to finish the sentence. Whatever you'll do with your fermentations will be insignificant. Thank you, good. The second one is, we have a global responsibility to stop releasing the most concentrated form of carbon dioxide as part of our activities, when we know we are contributing to the disaster of our own making. And let me finish with some acknowledgements. Firstly, thank you to the organising committee. I think there are people I don't even know on the organising committee, but I want to thank you as a committee for the invitation to come and speak to you today. I want to attribute acknowledgement of the protocol and the people, all of them, responsible for it, and the people who've joined it. And I'm proud to say that the Department of Viticulture and Enology at Davis is a signatory, and I hope they'll become a mentor, and I hope you will too. But this whole journey begins with a gift from a person called Robert Mondavi to build an exceptional winery. The Jackson family, in particular Jess and Barbara, were instrumental in making us get to be a LEED Platinum building when the university didn't understand why you would do that, and most people said, what a waste of money. Those are the kind of people that help us get to be LEED Platinum, that let me tell you about what we just did this afternoon. TJ and Valida Rogers were people that helped us build those fermenters, the most advanced research fermenters at the time. Jerry Law and his family made a contribution to help us finish the building. Many, many other people that made that building possible. So this is not a grant from industry, this is not a grant from government, and this is not university funding. So it is these people that made that possible. They understood the carbon capture, they understood the off-the-grid solar. That's why they helped us. The California Energy Commission funded the project with the used batteries, which are now in place. GE, Water and Secris provided the RO system that we use for rainwater collection. And I want to thank my colleagues and students at Davis. Thank you.